Okay, it's 3:02, so I'm going to start today's lecture. So I just want to emphasize that today's lecture will be a companion or sequel to the last lecture we had, lecture 6. So lecture 6 and lecture 7 are going to be tightly coupled, which is important for me to indicate this for anyone rewatching this through video. So last lecture, we started on the first half of the PowerPoint slides dedicated to JavaScript data structures. Let me get to the overview really quick. So we covered arrays, we covered stacks and queues, and we covered sets. So last time we talked, we got through the first 3 parts of this PowerPoint presentation. So today I'd like to finish these last 4 components. I want to talk about maps. I want to talk about iterator objects. I want to talk about spread operator, the spread operator, and destructuring. And then I want to talk about the built-in traversal methods that are in there for arrays. And I'll kind of explain why we want to know those and why those are important to cover in today's lecture. Let's see here. Okay, so I'm going to quickly jump down to part 4 as we have a recording already for parts 1 through 3. So we will immediately pick up where we last left off, because that's how recorded lectures work best. So let's see here. This is section 3 and section 4. Okay, so let's talk about maps. We've talked about arrays, we've talked about sets, stacks and queues and whatnot. So the first thing we're going to do in terms of talking about maps is we're going to define what are maps as they relate in JavaScript. We'll take a quick overview of the methods that maps have. We'll look into instantiating maps, check the properties of maps, and then we'll look at the getters and setters, how we access data from a map and how we can go ahead and set data into a map or mutate the state of the map. Then we'll look at various ways we can transform maps into other data types, because those are usually very powerful tools that are important to us to be able to use maps in interesting and novel ways. Okay, so maps in JavaScript. Well, maps are really similar to sets, actually. So a map is a keyed collection, just like a set is, but maps distinguish themselves from sets in the fact that there is an actual something. It's also could be called an associative array. There's something that's actually associated with each value inside of the map. So you have a key value pair. And so we can use the key to access the value. So interesting enough, maps distinguish themselves from index collections, because index collections, like arrays, the keys have to be integers, right? And the integers start at 0. So they start at a non-negative number and they go all the way up until however many indices you need inside that list. So maps are very much like that, but your key could be any type of data. And the value can be any type of data. So now the critical thing is that the keys do have to be unique. So maps are objects, just like sets are objects and just like arrays are objects. And so they have methods that define how we can traverse and set or get keys. So if we were to, or their values. So if I was to do a type of on a map, it would show that it is a data type of object. The types of its elements are not fixed. That's just what I said. So we can mix and match whatever we want in there. The sets are guaranteed to be dense, just like sets. Sorry, not sets, the maps. The maps are guaranteed to be dense, and the keys are guaranteed to be unique. So those are 2 things we can always count on in terms of a maps implementation. So let's quickly go ahead and talk about the methods that are going to be defined inside of maps. So there's a constructor. Then the accessors that we'll have is going to be a size, which is actually a property. Notice it is not a method. There's no parentheses. So this is actually just a data attribute, just like length is inside of Java. We have the has and get methods, which both use keys to be able to access data from the map. We have set, delete, and clear as our mutator methods. Okay, so how do we instantiate a map? Super simple. We just use the new keyword. We use the constructor name, which is map, and we can assign that into a variable. Here, I use the variable name dictionary, or the excuse me, or the abbreviation of that. We can also pass in a set of parameters into a map to go ahead and instantiate it. So if we do that, we can pass in an array. And in fact, we have to pass in an array with inner arrays. So a two-dimensional array, if you will, where each nested array is two elements, where the first element is a key and the second element is a value. So in this example, I have an outer array that contains two nested arrays. Inside those two nested arrays is a K1 that's going to map to the V1 and the K2 that's going to map to the V2. So the key and its associated value, the key and its associated value. So when I construct this map, this is going to have two elements, and it's going to map K1 to V1, K2 to V2. With no parameters passed into the map constructor, I would have a map that has 0 elements. Okay, so let's talk about properties of the map. Again, so far maps are pretty similar to set, with the distinguishing factor that the keys and the values are different, whereas in a set, the keys and the values were the same thing. So just like a set, a map has a size. And the size of a map is not fixed. It can grow and shrink, but it cannot be reassigned. So essentially the same rules that apply to sets also apply with maps. So if you want to empty a map, you're going to have to use the clear method. You won't be able to just overwrite or assign the value of 0 to the length like you can in a list. Okay, how do we get data out of a map? So just like sets, we do have the has method where we can pass in a key, and that's going to return true or false if that's if the map. It's going to return true or false if the map contains that particular key. So let's look at an example of this. Suppose I create the map we saw just previously. It's going to have 2 keys, and each of those keys map to a V1 and a V2. And then I can ask the map here, do you has key 1? Well, since it has that key, it will be true. It resolves to true. Now, it's important to know that has only resolves for the keys. It does not resolve for the values. So if I ask if it has a V1, which is one of the values, it's going to say false. It's only looking to see if the map has that key defined inside of it. In addition to has, though, unlike the set class, we also have the get method. And with the get method, we can pass in a key and return back the associated value to that key. So we're going to look at the same map again, and we'll ask for our dictionary to get the value associated with K1, and it's going to, right here, return back V1. Now, if I go ahead and create this map again and ask it to get the value, that's not how this method works. So it's going to say there's nothing defined as is that value, because it's trying to use V1 as the key, and there's no key of V1 inside this map. So we're going to return with the undefined object. Okay, so simple enough to access data. It's pretty similar to what we've seen before, with the one additional option to be able to actually extract data out of our map. How can we go ahead and mutate the state of the map? Well, pretty similar to sets. So as opposed to add, though, we have a set method for maps, and the set method actually has 2 parameters where you give it a key value pair. So if I create an empty map, like right here, a new map, I can then say, okay, dictionary, set K1 to be my key and V1 to be my value. And you'll see what resolves after that is going to be a map now with 1 element, with 1 entry, and that entry is going to have K1 mapped to V1. So it's a key value pair. If I want to delete an entry from my map, I can call the delete method off of the my dictionary, and I pass it the key for the key value pair I want to remove. So suppose I had this map here. I'll just go ahead and inspect the map object I already had in memory. It has K1 to V1 and K2 to V2. I can then ask my dictionary to delete K1. It's going to resolve and actually respond, either return a value either true or false. True if it successfully deleted the entry, false if it could not find that entry to delete. This resolves to be true. And so now if I go and inspect the state of my object after that invocation, it will show it now has one entry, and that entry is the one from K2 to V2. So it removed the K1 to V1. And then clear removes all of our key value pairs. So if I have this map that has 2 entries, I can tell it's a clear. This does not have a return type. So whenever you see undefined inside your console log, it just means that that method doesn't return anything. All methods by default actually return something, but if it doesn't have a return statement, it just returns an undefined object. That's what's happening there. And then after that, I can go ahead and inspect my my map, my dictionary, and now it has 0 entries. So empty map. So we talked about how to access data. We talked about how to mutate data. We talked about how to instantiate maps, and we talked about what maps are. Really powerful data structures. Let's talk about how we could transform maps to arrays and arrays to maps. So if I wanted to take an array and convert it to a map, we've already seen that. That's what we use the map constructor for. So I'll just go ahead and repeat this example that I've already given. If I wanted to take a map and convert it into an array, the class actually has a method called from that allows me to pass a map into it. Just like this is actually the same method we use to actually convert strings into arrays as well. So here's an example. I'll take this map right here, my dictionary map that is already in memory, and then I will pass it into array.from right here, and it's going to resolve to be an array with 2 array elements. And in fact, one nice thing about the dev tools is I can actually unpack these individual nested arrays and see what they contain. And in fact, I see it contains at index 0, K1, V1, and index 1, K2, V2. So I can see that it converted this map into the same type of parameterized 2D array that we could use to construct a map. I can also use the spread operator to transform a map into an array. I'll talk more in detail about what the spread operator is later in this lecture, but just know if I have a map object, and here I see I have my dictionary, I go ahead and inspect it to see it is indeed a map. I will then use the spread operator on map, and I will nest that or scope that into the square brackets for a list. So inside of a list, I will spread out the contents of the dictionary, or unpack the dictionary, and what that's going to do is actually unpack it into a array. The same thing array.from does. This is just, in my opinion, a cleaner way of doing this. And so again, we're going to learn more about the spread operator later on into this lecture. And if I want to take a map and transform it into an object, which we'll talk about next lecture, I can, from the object class, use the from entries method and just pass in my map. So if I have my map, I'll just inspect using my console tools. I see it has 2 entries. I will pass my map instance into object.frame entries, and you'll see it turns it into an object. So this might not, so notice that objects and maps have a high correlation. Objects in JavaScript are actually just key value pairs, but they're more primitively scoped. So maps are kind of a data structure version of what's happening with objects. So again, we'll look deeper into objects next class when we talk about objects, classes, and inheritance, when we start talking about OOP with JavaScript. Okay, that's enough with maps. We'll revisit maybe the concept of maps when we start with generic objects next class, but I want to move to iterator objects. So iterator objects, I want to cover like what are iterators in JavaScript. I know that you talked about iterators in Java 2. So we'll kind of distinguish JavaScript iterators from Java iterators. We'll do a quick method overview, super simple. We'll take a look at what the next iterator does. I mean, what the next method in an iterator object does, and then we'll look at examples of instantiation and usages of it. So iterator objects in JavaScript. Quick explanation. Iterator objects iterate across a sequence. Iterator objects may return the value at its current position, and iterator objects track their status within the sequence. So that's pretty much the responsibilities of an iterator object. It's very similar, if not the same, as what you learned what iterators do in Java. So what are advantages of using an iterator object over just using like a traditional for loop or for of loop or for in loop or all the other ways that you can manually iterate over a data structure? Well, there's a couple. The first is you can have multiple iterator objects that can be instantiated on top of a single sequence. So if you needed to be able to iterate at different times, you could track each individual iterator as you need to. So that gives you very powerful control without having to configure that manually. Iterator objects do not mutate the state of the sequence. So they're autonomous and separate from themselves. And also, all iterators get values with its next method, regardless of the underlying data structure. So iterator objects, one of the goals of iterator objects is to make it easier to extract data from data structures, regardless of how you would normally access that data. So I spent a lot of time talking about lists and sets and maps, and they all access data differently from within those data structures, from within those containers. And so one nice thing about an iterator is it gives me a universal approach to extract the data back out, regardless of how it would normally have to get dereferenced. So let's take a quick look at method overview of iterators. So iterators, and I believe this is the same way with Java, they are, you don't typically construct them or instantiate them directly from the constructor. You use what's called the factory method pattern, or use a factory method. So you're using the factory pattern. So essentially what happens is there are three methods that are defined inside of our data structures, inside of arrays, inside of sets, inside of maps, that can be invoked on any one of those data structures to instantiate an iterator object. So keys, values, and entries are the three methods that our data structures that we've looked at thus far have built in. And when you invoke those, it will return to you a new iterator object. And the iterator object itself only has one method. It's the next method. The next method is both the getter and the setter. It gets some data and it mutates the set of the iterator. And so here, I just want to highlight that a factory method constructs and returns a new instance of an object. So let's take a look at our next method, and then we'll look at ways that we can actually use iterator objects. So the next method, let's see, iterator objects only have a single method next, right? The next method returns an object that has two properties, a value property and a done property. The value is whatever the current element that's being tracked by the iterator, and the done is a Boolean value that indicates whether there are whether there are more items in the sequence. So it lets you know whether the iterator is done or not. So as I said previously, next is both an accessor and a mutator method. The thing that it accesses is the data from the iterator. The thing that it mutates is the state of the iterator. It moves the next current element in the sequence as soon as you call next. And so next easily accesses data from the sequences in one of two ways. It avoids concerns from the underlying data structure of the sequence, and it also avoids concerns for the size of the sequence because it always returns an object with those two properties, what the current value is and whether it's complete or not. So let's see what this actually looks like. So let's take a look at keys. Keys is going to return an iterator to access a sequence's keys. So what does it mean for an array to have keys? Well, even though we said that sets and maps are keyed collections and arrays are index collections, and in all honesty, and the way that it's actually implemented probably in the back end of JavaScript is that the index, it represents the key to access each value. So if I create this array right here that contains the elements A and B, and then I go ahead and ask this array to generate a iterator object for the keys items, and I'll bind that to just a iter I'll call my iterator object iter here. And notice once I do that inside of my console, it does show it produces an array iterator. So once I have that, remember my iterator object only has one method called next. So if I invoke that method called next, it's going to return this object with two attributes, a value attribute, which is the index of 0, the key 0, and done. No, it's not done because there's another thing that I can iterate on. So I invoke iter.next again. Now I get the value of 1 for the key, and done is still false because I will continue to iterate until I get a value that's undefined. So if I try to do that again, iter.next, I get a value that's undefined. I no longer have keys inside of my list, and therefore done becomes true. And if I were to continue to hit iter.next, it will continue to say value undefined, done is true. So a nice thing about iterator objects is you will not cause exceptions or cause erroneous behavior by constantly trying to index after the fact. It guarantees to give you a valid object, and then you can use this attribute to toggle out of whatever logic you're using to repetitiously grab these elements. Okay, so let's see how that compares with keys. I'm sorry, with sets. So let's invoke the keys method on sets to get an iterator object. So looks very similar. I'm going to create a new set. I'm going to save it to, I don't know why I called it vals. I should have called this keys, but that's okay. So I'm going to have a set of A, B. I will use the keys method to get the iterator object. And notice here it's going to say a set iterator for A and B. And so remember, the interesting thing about sets is that in a set, the keys and values are the same thing. And so if I go and query my iterator object to get the next thing, it's going to return the value of A, and done will be false. I do it again, I get the value B, done false, I do it again, and here I'll finally get undefined, and done is true. So here for a set, the keys and values are the same. For a map, you could probably expect it should give me just the keys. So let's just take a look at that. I'm going to create just an array here. I will then pass that array into the map constructor to create a dictionary. I indeed see I've instantiated a dictionary here. It has two entries where K1 maps to V1, K2 maps to V2. From this dictionary, I will invoke the keys method to generate an iterator object. And here I can see that a map iterator has been constructed. It even shows me what it's going to iterate over. It did the same thing here when I did that for the set iterator. The only time it won't do that in your console is when you do an array iterator. And so, in fact, when I go and do iterate.next, it's going to give me the first key. If I do iterate.next again, it'll give me the second key. If I do iter.next again, well, there's no more keys, so it becomes undefined, and done becomes true. It has nothing more that it can iterate over. I've consumed all of the elements from the iterator. Okay, so I'll go more quickly through these. Values is the same thing. Values returns an iterator to access the sequence's values. So if I had an array and I invoke the values method to get the iterator object as I iterate through using iter.next, iter.next, iter.next. Again, notice how nice this is. Once I have an iterator object, I'm only ever doing the same thing with it to get all these values. That was a highlight here, right? Before is that I'm getting these values here, here, and here, all using the same method calls. So it makes for nice and easy coding in terms of how you access data from your data structures. Anyway, going back to here. So for my values, this time the values in my list is going to be the actual content. So it's going to be A. If I go ahead and invoke next, it'll be B. If I invoke next again, it goes to undefined, and done becomes true. And so very similar, if I were to look at my set, but get the values iterator for my set, well, the keys and the values of a set are exactly the same. So as I iterate on this iterator object for this set sequence, it's going to give me the A and the B. And all the way until I get an undefined, because done is true. And then for a map, you can anticipate that if I go ahead and build a values iterator object on this map, which is the same map we looked at before, it has K1 to V1 and K2 to V2. the iterator object will iterate over just the values, so v1 and v2 in this map iterator. So if I have my iterator object that I called iter, go to next, it will return v1. If I do it again, it returns v2. If I do it again, it returns undefined, with done finally being true. Now suppose that I want to be able to get both the key and the value. Well, that is what entries is for. It returns an iterator to access the sequence's key value pair. So for an array, that'll be both the index and the value. So suppose I had an array that I implemented here, and then from that array, I go ahead and instantiate a iterator object to traverse it, to iterate across it. Well, here's my array iterator. If I then have this array iterator object, if I invoke next on it, notice now it's actually going to return an array of 2 elements along with done is false. And so one nice thing about DevTools here is I can unpack this array, this nested array inside of my object and actually inspect it. So if I unpack this, I can say the value is a 2-element array that has 0 as the first index and A as the second index. So it's key value. And so if I then iterate again, I get another 2-element array where the first index is the key of 1, the value of B. And then if I do that again, next, I get undefined and done is true. And then if I was to do that with sets, this is where it gets a little bit interesting. And I proved something I've been claiming this entire time, that in sets are like maps, but the keys and values are exactly the same. Here we get to actually illustrate that. So I'm going to create a set that contains A and B, or A comma B. From that set, I'll just call it items. I will then go ahead and produce an iterator object by invoking the entries method. I will save that iterator object to iter. So it shows that I have a set iterator where A maps to A and B maps to B, because the key and the value are the same in a set. So you can think of a set as a special case map, really, where both the key and the value are always the same. Kind of like 2D is a special case of 3D, where the z-plane is always equal to 0. Okay, so anyway, on this iterator object, I can invoke next, and it's going to do the same thing. It's going to give me this 2-element array, and where the first, where the key is A, the value is A. I invoke that next method again, and then I get the next key and the next value, and those are going to match. So I don't really get any interesting information from doing entries on a set, except for the fact that I can very much illustrate that key and value are the same there. And then for a map, this is where it's a little bit more interesting, I guess, also with the list. Here, if I create my map like I did before, and then invoke entries to generate an iterator object to return the entries on each of my entries inside of my map, I will get the key value pair each time I call next. So K1, V1, K2, V2. And then if I call iterator again, I can go ahead and get undefined, and I can get done equals to true. Okay, so that's pretty much how iterators work. I'm pretty sure that's almost exactly as they work in Java, although I think the syntax here is a little bit easier because we're in a loosely typed language, so you don't have to worry about defining generics. Okay, so next I want to talk about the spread operator and destructuring. So first I'll explain what it means to destructure, which this seemed like an apt set of lectures to talk about destructuring since we're talking about data structures. I'll talk about the spread operator as it's declared on how to use a spread operator to declare functions. I'll talk about how to use a spread operator on arrays and objects, and also talk about how to use a spread operator to invoke functions. And while we go through these examples, I'll also talk about how we can destructure some of this stuff too. So let's talk about explaining what does destructuring mean, because I don't know if Java has an easy way to do this. Python does, JavaScript does. Java, you might not have encountered something like this before. So a destructure assignment is simply an assignment where we unpack values from an array or the properties from an object into distinct variables. So essentially, it's this case where we might have a collection of values inside of our array that we want to declare to individual variables. We can destructure the array, essentially break it down and save the individual values in the array to labeled variables. So, or we can do the same with objects. We can go ahead and take values out of an object, properties out of an object, and assign them into individual variables that we can then mutate and access them. And because of this destructuring method, we can use this to do all sorts of things, cool things that you've kind of seen before, where we can start merging data structures together by unpacking them and combining them into a new data structure, or we can start extracting some elements out of a data structure so that it's only a subset of its original properties or a subset of its elements. And I'll show you how to do both of these in this part of the lecture. And then the spread operator is used, when we have multiple elements from an object or an array that need to be dereferenced and packed together or included together. So let's see what that actually looks like in practice. So here, let's use the spread operator to declare a function. And so you might have seen something similar to this in Java. You probably covered this when you covered arrays in Java 1. It was the variable length parameter, so that you can pass in any number of values and they kind of get packaged into an array for you. So suppose I declare this function here called foo. And then here, foo will have a spread operator in front of the variable name. By putting the spread operator in front of the variable name, it allows me to have an arbitrary number of values that gets passed into this function. And all these values get grouped together into an array, essentially. So if I were to do console.log on what this parameter is, you're going to notice it's going to be different each time I invoke it. So here, let's invoke foo with no parameters. You'll see when I go and the console.log executes, it shows actually an empty array. If I pass the value of 1 in here, it will print out an array that has the value of 1. If I pass 3 values in, notice my array has grown to contain 1, 2, and 3. So essentially, the spread operator, when it's declared inside of a function's parameter list, allows you to carry a variable length parameter and bind those together as if you were passing in a list or an array object. Now, the big thing to know about a spread, the spread operator as a part of the parameters is it's got to be the last parameter. So you can't have more than one spread operator in a function parameter list, and when you define it, it's got to be the last one, because it's going to, because you can nest if I wanted to. I can't show you here, but if I wanted to, I could do it here. I could declare, oh, don't want to lose my T. If I declared my function here, function foo, I could have had like an X, I could have then done a Y, and then I could have done like a rest like this, and that would be fine. And so when I go to invoke this, I could give the first value that would be supplied would default to trying to set the X value. The second value that gets supplied into the parameter list would be the Y value, and anything thereafter would be associated with the rest. So you can mix and match having a spread operator for the variable length side of a function along with specific valued parameters. Okay, so let's talk about how we can use the spread operator and this concept of destructuring on both arrays and objects. Arrays and objects are probably the two most primitive data types, the data structures that we have available. And so by primitive, it means that we actually have like literal ways of creating them. We learned how to create a literal array type by just using the square brackets. If we use the curly braces, which you'll see on the next slide, that's a literal way of defining new objects without having to use a new keyword, without having to use a constructor. So that is kind of a sign that those are like our primitive container types to hold and maintain data. So let's first look at how we might destructure an array. We talked a lot about defining an array, so now let's talk about breaking one apart. So suppose we had this array that contains the value of 10 and 20. I could destructure this and bind the 10 to the A value and the 20 to the B value by first I have to declare a variable, lit A comma B. So I'm defining two variables. And if I want to destructure, I'm actually destructuring by putting the two variables I want to have assigned those values in between the square brackets. So the same way you would normally kind of declare or construct structure an array to begin with, we will use that to destructure our array. So after I'm done this assignment, this destructuring expression, if I go and then inspect what is the value of A, you'll see it actually has a value of 10. And if I go and then say, okay, what is the value of B? Notice it is defined, it has the value of 20. So what I've essentially done was taken this array and rip it apart to give A and B a value. And now if this was saved to a variable, I would still have the array contained as it were, but I'd have these individual values that I could process on, I could do whatever I want, and it's not actually part of the array itself. Now, suppose I want to destructure and I have more than one thing, and I want to get the remaining units packaged together that I did not grab out of the array. So suppose I want to destructure like this. Again, every time I destructure, I'm going to declare a variable type. I assign all the variables I now want to have meaning inside of a set of square brackets. Here, I want to have the first value be A, the second value be B, and then everything else, I'm going to go ahead and use a spread operator to group the remaining elements together and capture them as a new array with just those elements. So I do my assignment here, and then I'll go ahead and here I have an array literal, but this could have just been a variable that also maintains an array. But here you can see this 10 should go to this A, this 20 should go to this B, and the 30, 40, and 50 should map to this rest that has the spread operator. And in fact, if I go and inspect the values of A, B, and rest inside of my dev tools, you'll see that it does indeed have 10, it does indeed have 20, and then rest has the subarray of 3 elements, 30, 40, and 50. And then, so let's talk about doing the exact same thing, but instead of arrays, let's look at objects. Now, I know you haven't seen objects before, but fortunately, objects and maps are pretty much the same concept. They are a key value pair. The difference is that objects are the more primitive data structure in JavaScript, and so we have a literal a literal initializer or a object initializer, just like we have a list initializer. So we use curly braces to initialize an object without having to use a constructor. We can use a constructor, which again we'll talk about next lecture, and we can just define the key value pairs. So here's an example of a literal object that has the key A and the value 10 and has the key B and the value 20. Now, suppose I wanted to destructure this object so that I had individual variables of A and B that have the values as they were in the object. Then I first of all have to use a variable keyword like lit, and then in between the curly braces, same way we structure our object, we're going to destructure our object and pass in the names of the keys we want to get values of in the local space or the global space or wherever we're actually operating in. And so after I do this, if I go and inspect my A, I'll notice, hey, it has the value of 10. And if I inspect my value of B, hey, it has the value of 20. And again, I can destructure an object the same way I can destructure an array, so I can use the spread operator. So suppose I had this much larger object that had a key of A that has the value of 10, the key of B that has the value of 20, the key of C that has the value of 30, the key of D that has the value of 40. Then I can destructure it by having the two keys that I want to extract and have locally, A and B. And then I can create a rest. I can use the spread operator, and there's some variable name. It doesn't have to be called rest. It could have been anything. I could have called that, other or whatever, X. So this isn't a keyword. The big thing is a spread operator. And then after I go ahead and do this expression here, I can go ahead and inspect the value of A is in fact 10, the value of B is in fact 20, and now the value of rest is a object itself that only contains those things that were left over. So if I wanted to get an object that removed elements, this is a great way of doing it. If I wanted to get an object that added elements, I could do that as well. Actually, you'll see that on the next set of slides. Yeah, so far here, I want to highlight, so far in these first two slides, whenever I use the spread operator, it was on the left-hand side of the assignment operator. That means it was in the writing side. That means it was creating an array here, and it was creating an object here containing the things that were left over that weren't destructured and put into its own variable space. Let's see what happens if we want to use the spread operator on the right-hand side to read our data in as a set of values. We could do that as well. So let's look at array destructuring with the spread operator here. So first, let's create an array. We'll call A that contains the elements 10, 20, 30. Remember, what the spread operator essentially does is it unpacks a data structure and lays everything out as an individual set of elements, or it can pack a set of values into an array. So when you're unpacking a data structure, it's going to set it as a set of individual values itself. So again, we can use the spread operator to destructure a pre-existing array. So if I want to make a flat array, that means the array doesn't contain a nested array itself. I can unpack A, so it has 10, 20, 30, and then comma 40, 50. If I then inspect B, you'll see I have a flat array that has 5 elements. So I unpack this array of 3 elements and laid them out to be on the same level as the 40 and 50. So 10, 20, 30, 40, 50. And notice I can do the same thing with objects. So suppose that I create this object that has a key A with value 10 and a key B with value 20, and I want to create a more complex object with the object A. So this object B, I'm going to create a object literal, right? I have an initializer with the curly braces. I'm going to unpack all the values in A, then do comma, and then add a new value. And the result of that is going to be a more complex object that has now 3 keys and 3 values, and not something that has a nested object, for instance. And so the last thing I kind of want to talk about in terms of the spread operator and destructuring, at least for now, before we hit objects proper style, is how do we invoke functions with the spread operator? And so I'm going to give you some use cases that actually makes a lot of sense and will be useful for you to know. So one of the standard libraries that you get, and we'll talk more about this on the lecture where I go into the standard libraries that are available to you, is the math standard library, so the math class. And so the math class in JavaScript is very similar to the math class inside of Java. So we invoke the methods using math, and we don't instantiate an instance. We can call it all these methods directly from the math class itself. Math class has 2 methods, a min and a math class, a min and a max method that, giving a sequence of values, will tell you what is the min of it, if it's the min method you called, or what is the max. So again, these are variable length arguments that are supplied in here. So I can put in any string of numbers and it will tell me what is the min value, 1. Same thing here. For max, I can put in any string of numbers, sequence of numbers, and it will tell me what the max value is, the min value. Now, most of the time, this is not how you maintain numbers, right? That's not in any kind of data structure. Normally, you're maintaining your numbers inside of an array. But the problem is if we pass the array into our min method, well, the array is not a number, so it's just going to let you know nan is your min value because you supplied me with 1 argument and it wasn't a number. Same thing with the max. So this becomes problematic when you want to use built-in tools that are expecting variable length arguments, and you want to supply it with something like an array, and you don't want to normally have to like break through and use like a for loop or manage having to figure out how to break this down. This is one instance where the spread operator can do that for you. You can take the pre-existing array, break it down, into a collection to be the equivalent of a collection or sequence of values that are unpacked and not structured anymore. And then it could pass that into this parameter for min to give you the value of 1. We're going to pack this array to look at all these individual values and give you the value of 4. And I'll come up with other use case examples as well, but this just becomes a really potent thing at your disposal that I wouldn't be surprised if you end up having to use sometime this semester, simply because finding min and maxes can be used for all sorts of interesting computations. Okay, so we talked about maps, we talked about iterator objects, and we talked about the spread operator and the destructuring, how to structure data in JavaScript. So the last thing I want to do is talk about the built-in traversal methods for arrays. And the big reason why I want to talk about this is these are very powerful. They're categorized in one of two types of functions. They're first-order functions. They have high-order functions and high-order functions and first-order functions, which I'll explain in just a moment. And it's worth learning what these are because it'll make you a more powerful programmer, first of all. Second of all, you'll understand how to start unlocking the functional programming paradigms of JavaScript. And third of all, when I was talking about this class to some recruiters, they told me that some of these methods are sometimes used for interview questions. So that really behooves me to go ahead and spend more time to explain what they do. So if you're asked about them, you understand how they work. So I'm going to categorize the built-in traversal methods that are given to you inside the arrays class as searchers, iterators, sorters, simplifiers, and existential quantifiers. These are my own brandings to try to break this big collection up to be a little bit more manageable based off of the tasks they do. If you think of better names, let me know and I can reclassify them. But I think that these are pretty sound names for what these things do. Okay, so I'm going to break down and we'll look at what the searchers do, the iterators do, the sorters do, the simplifiers, and these existential quantifiers one by one, or by category, and then individual examples from there. So let's look at our searchers. Quick overview. We have 5 searcher methods that are defined inside the arrays class. Index of, last index of, includes, find, and find index. And I can automatically break these down into first order functions and high order functions. We should talk about what this is because this is not something that happens in Java. This is something that can happen in Python. This is something that can happen in JavaScript. And the concept of a high order function is pretty critical in both these scripting languages and pretty critical if you're going to look for a job. Again, this is going to be a notion that they're going to want to make sure you understand. So a first order function just means it's a function where where values are passed in as parameters. So you pass in an individual value, simple enough. A high order function simply means it's a function, just a normal function where one of its parameters is a function itself. And that's what makes it a higher order function. It's a function that operates on other functions. Whereas this is a first order function. It's a function that just operates on data. So don't let the terminology kind of confuse you. These are pretty easy concepts in terms of what they resolve down to. So let's take a look at what these functions do in terms of the searchers. They obviously search for things. So the index of takes in a value, returns the first index of an item in an array. So imagine if I have this array here that I defined, right? A, D, B, C, B. Okay. If I invoke on this array the index of, and I pass it in a value, it will give me the first index of that value. So there's 2 instances of B here, right? So it's going to find the first instance and give me that index right there. Last index of does the opposite. It'll give me the last index of the array of where a value is. So let's do the same thing, create the same array, but on this array, invoke last index of, still passing in B, but this time it's going to give me 4 because it's going to give me this index. Unfortunately, that is, in terms of finding the indexes using these approach, what you're going to be locked to. You can either find the first or the last. If you have more than that, then hopefully that does not matter. You have to use another approach to filter it down beyond that. So These methods are just simply there to get you this one or this one. And then finally, we have an includes where we can pass in the value, where here we can ask, does this array include a B? If it does, it will return true. If it does not, it would return false. So that just returns a Boolean value on whether the item is in the array or not. Again, I think these are similar to the same kind of methods you would expect in an array list inside of Java. Let's take a look at the high order functions, because this is probably something you're not familiar with looking at. So for the searchers, there were two high order functions. There was the find, that's looking for a function to get passed in, and the find index. So the find is essentially going to return the first item that meets the condition given from the given function. And the find index will return the first index of the item that meets the condition from that given function. So I want to show two different ways that you can do this, where you can either pass in an anonymous function as a parameter, or you can pass in a named function as a parameter. After I show you how to pass in an anonymous function, I will, for the rest of my slides and most of my labs, and for the rest of the labs, use named functions because I like to name things. It makes debugging things way easier when you don't just have a giant anonymous function, right, being provided as a parameter. So I will show you, because you will see code in the wild. You will be with coworkers who define anonymous functions. For some reason, it is a very common practice to use anonymous functions in JavaScript, and that is something I hate. I want to label everything. So I'll show you this so you can read it, but I want you to do the right-hand side. The right is right, left is what I do not prefer. So let's take a look at here. We have R is the array that we've been looking at. Here, I'm going to invoke the find method. And now remember, the find method requires a function to get passed into it, not a function to get invoked into it, a function to a reference to a function. So if that function doesn't exist already, I can define that function in scope. I can either define it as you would traditionally define a function, or I can use a fat arrow function. For brevity's sake, I just use fat arrow functions, which we defined inside the function area in the basics Java lecture that we had before. So here we can say, we can see that this function set has a parameter of x, and that x then is used to return whether x is greater than b. And so remember, we can use a relational operator with strings. And so the instance where it's going to find where this is true is, it won't be A, it'll be D. So it's going to return D. And so here I'm going to do the same thing, but I'm going to name my function first, right? So I have this fat arrow function that I am then assigning to the name foo. And then I'm going to create my array, and I'm going to here take, and I'm going to say array find using the function foo. To me, this is much more readable, especially if you use a name that's not foo. And so notice I'm going to get the same results here. In fact, this is the same implementation, only I assigned this a label and then passed the function by label, as opposed to just defining an anonymous function. But again, I think this is more readable. And so I'll show you the same thing with find index, which will return the index of, and so we're using the same function here. So all I'm doing is changing the function call. So instead of returning D, I'm returning index of 1. And so I'm doing the same thing here. Okay, let me move over. So we are done with searchers. Let's talk about the iterators we have. So with our iterators methods, we have no first order functions, so ones that just use parameters. We only have the high order functions, or those that use functions, that are functions that depend on functions to get passed to them. So let's take a look at the ForEach function. ForEach function is unique from all the rest of the functions available to us, as it can actually be used on arrays, sets, and maps. So you can actually use ForEach as an iterator. So in addition to having iterator objects, you can also use the ForEach method on all of the defined data structures in JavaScript. Now, there is no what's important to note here is that for each does not have a return type. So don't anticipate it to return back any data. So far, all the functions we saw return back like an index or a value. For each is really designed to execute a given function on each item in the array or set or map. So don't expect it to give you back data from this call. It's used just to process the data by just invoking for each. So let's take a look at what that looks like. I'm going to create a function here, fat arrow function. The order in which the parameters get passed is the value followed by the key. And these are optional. You don't have to have these on here. You could use just one, just the value, or you could just use the key. But if you want to use just the key, make sure you have two arguments so that the second one actually gets passed in. So in this function, I'm going to look for the value and the key, and I'm going to respond to that by just console logging it. That's all this function does. It's console log of V and K. And so I'm going to create an array that's A, B, and C, and then I'm going to call on that array for each. I'm going to pass it this foo. I'm going to pass it this method, and notice it's going to execute and give me the value and the index. The value and the index, the value. It's going to process that function on every element inside this array. And so if I do the same thing, define the same function, create a set, and then call for each on the set, passing that function, it's going to do the same thing. It's going to give me the keys, the values, and then the keys. And then if I create a map with the same function and call for each, passing it that foo function, I'm going to get the same output, right? The values and the keys. So if you need a quick and easy way to iterate over any type of data structure and process on it, then the for each method is a powerful tool for that. But like I said, it does not return data. If you need to have data returned back, then the for each method is not what you're looking for. It's actually the map function that you're looking for. So the map function, again, another high order function, because we have to pass it a function that we're mapping on top of our array or a list with. So what the map does is it returns a new array with the return results from a given function. So imagine if, for instance, I had this function foo, and it was the same function I defined before. I pass it a value in the array. For each value in the array, I say, is that value greater than B? So that's going to return either true or false. So then let me declare the array. I'm going to do the same array I had before, A, D, B, C, B. And then on this array, I'm going to invoke its map function, and I'm going to pass it the foo function to process on each of these elements. Now, what's great about the map function is it's going to create a whole new array based off of the result I get from this function. So it processes some meaningful data. So here, I started with a 5-element array of strings. I'm going to get back a 5-element array of Boolean values, where it's going to say whether it's true or false if X is greater than B. And you're going to see when it's A, it's false. When it's D, it's true. When it's B, it's false. When it's C, it's true. When it's B, it's false. Very powerful method. I expect that you'll likely use this map function. And do not confuse map with a dictionary of map, right? It's like mapping a function on top of a data structure. It's unfortunate we have two different names to mean two different things. Then we also have flat map, which is very similar to map, but it has the advantage where it can also flatten arrays that are produced from the given function. So sometimes there might be the case that, imagine, and maybe this was a bad example. Maybe I should have come up with an example of numbers, but I want to stick with the same array so that I didn't have to define what the array was each time. So imagine if I have this function that I pass an X. So for each element inside of my array, I want to check and return back an array where the first index, or index 0, the first element, or index 0, is whether X is greater than B, and the second element, or index 1, would be whether X is less than B. So each time we invoke this function, notice what it does is it doesn't return back a value, it returns back an array itself. So let's see what would happen if we call our map function on a function that we provided that's returning back an array. So we're going to do our same thing, A, D, B, C, B, and notice what I get back is an array of arrays. And so this is fine, but maybe you don't want to have nested arrays. Perhaps what you want is the end result to just be a collection of a flat array, where it's just one array that contains values. And so that's exactly the distinction between map and flat map. So flat map will take the array that's produced by the function and it will flatten it so it's all on the inside the same outer array. So again, let's take a look. This is the same function, foo, where I take in an x and I'm going to generate two values and I'm going to structure them inside of a array. I'm going to operate on the same array elements and I'm going to invoke flat map instead of map and pass in my function foo. And so the result is, instead of 5 elements that are each an array of size 2, I will instead have a one-dimensional array that is 10 elements large, where this is the false true from the first invocation, right, of this array. This will be the true false of this array. This will be the false false of this array. This would be the true false of this array, and this would be the false false of this final array here. So it might be the case where you need to do this because maybe you'll then go ahead and process this in some interesting way. And so instead of having to add additional logic, you just have this method that you can invoke. Okay, so we talked about that was our iterator. So that was the ability to iterate over our data structures. And we talked about our searchers. So the next thing I want to talk about is what sorting options do we have for arrays? Well, there's two. We have a first order. I call first order. It actually doesn't use any parameters. Reverse. And I have a high order function, which is a sort, which takes in a compare function as a argument. Now, if you can leave that blank, and it does have a default behavior, so you can see what the default behavior is. And if you don't like it, then you can explicitly custom make your own compare function. So let's take a look at these. So the reverse method reverses the order of items in the array. So if I had this set of items here, right, A, D, sorry, let me get some order. So if I have this array A, D, B, C, B, and I reverse it, then it's in reverse order. B, C, B, D, A. Okay. Oh, let's look at the compare method. So when I define a compare method, you define compare methods exactly as you would in Java, which means that your compare method, when it compares between two elements, two values, it will produce a negative value, a 0, or a positive value. So let's take a look at this, because I'm going to illustrate how I can define the compare method in two different ways and produce two different sortings. And I decided not to use integers because that's easy. I decided to use text data because I think that's more meaningful. So here, this is what I'm going to do. My compare method is here. It takes in an A and a B. And then what it does is it's going to see, is A, so I use this, the conditional operator here, right? It's a ternary operator where I can evaluate this thing. And if it's true, I return this. And if it's false, I return this other thing. So I say, is A less than B? And if A is less than B, then I will return a 1. So that means that A is smaller than B, then that's 1. If A is not smaller than B, then I will return -1. That means, so I produce a 1 and -1. I don't produce a 0. Well, I do kind of produce a 0 because I'm not doing equal sign. So if it's the same, then it's automatically going to just, it'll switch order. So it implicitly computes for 0 computations is my point. So let's actually test to see if this is true. I'm going to create an array of A, D, B, C, B. I'm going to call sort on my array, and I'm going to pass it this function right there, my compare. And notice, if A is less than B, if I return 1 in that state, I'm going to sort from greatest to less, right? That should make sense. Because I'm saying A is less than B, I'm producing a difference of 1, which means that B is the larger thing, then A is the smaller thing. So, and then if I reverse this, if I want to sort based off of A is greater than B, returning 1, otherwise return -1, I can get the lesser element to sort first. So I can either have typical sorting or I can have reverse sort. And I can control that based off of my compare function. In fact, I can do something really wacky with my compare function. Like since I get to define the compare function, I can sort based off of a random number between 1 and -1, right? And that technically is a sort, but it's just a random sort. Okay, so that's good to know. So sort, so a very good question. How are the parameters A and B are passed here? So one thing to understand is when sort as a method is invoked, it requires a function to be passed to it. And so sort actually has a specification that it needs to have two parameters in the function that gets passed to it, an A and a B, or whatever you want to call it, an X and a Y, a param1 and a param2. Doesn't matter what those labels are, right? Those are just naming purposes for us. But the point is it needs to have a function passed to it that gives it two elements to compare to one another. And then when it's given a function that defines the comparison between two elements, it then iterates across your entire collection and uses the sort method on the compare between all the elements. Does that make sense? And so that's one of the specifications of the sort method itself, is that the function requires you to have two arguments. So it would not work if you provided a function that just has one element, or no elements, or no parameters. Okay, let's see here. Okay, so let me talk about next the simplifiers. So simplifiers have one first order function, so which doesn't actually require any parameters, so it just kind of got grouped in there by default. And then I have the rest are going to be high order functions. So filter, reduce, and reduce right require another function to get passed to them. So simplifiers are essentially going to be methods that take whatever your structured data is and simplifies it in some way. That was my goal in terms of using the term simplifiers. So to flatten, to filter, to reduce, or to reduce right are all going to simplify our data structure in some novel way. So flat is just like what flat map was doing. Suppose you have an array that itself contains a collection of arrays. So if I go and if I execute this expression here, you'll see that this assignment is going to show I have 5 elements. Each one contains a nested array of one element. So if I call flat onto that array, it's going to unpack all those nested arrays to be part of the outer array. And so this was super simple since I didn't put any more than one elements, but if I had more than one elements, they would all be on the same level. So this is just a great and easy way to unpack arrays so that they're completely linear. Filter, it allows us to return a new array that contains all items that meet some condition. So let's go back and create a function. So I try to use the same array for all these examples. So here I'm going to create a function foo that, given an element x, will check to see if x is greater than b. So here filter isn't, so even though this is a true or false, what it's actually going to do is it's going to return the element when this condition is true. So let's look at our array of A, D, B, C, and B, and let's call on our array the filter method and pass in this method foo on that. So we're going to evaluate, is A greater than B? No, it's not. So it's going to get filtered out. It's not going to be part of the returning array. Is D greater than B? It is. Is B greater than B? It's not. It's equal to. Is C greater than B? It is. Is B greater than B? It's not. So the returning array that I'm going to get back from this filter method is going to be an array that contains D and C. So notice this is a very powerful tool to be able to filter out filter data out of an array with more values. So if you need to go ahead and reduce an array down for a particular subset of values, the filter method's great for that. Okay, let's take a look at reduce. So reduce returns a singular value from a computation on all items from left to right order, and reduce right is going to do the same thing, but it's going to go from right to left order. So it returns a value from a computation on all items from right to left. So just to make this easy, I did concatenation, but you can imagine how this might be expressed in a variety of ways. So imagine if I have this function foo that takes in an x and a y, and it takes the x and adds it to the y. So again, just like sort requires two values, reduce, to be able to reduce it down, is looking to operate on like element 1 with element 2. And then the result of that with element 3, and the result of that with element 4, and the result of that with element 5. And it's going to go from this order to this order to this order to this order to this order. Whereas reduce right would start with B, then go to C, and then collect these, and then process this, then take the result of this, process this with D, take and process all of these with this last one. So it's essentially doing these cascading calls to simplify or reduce the contents to one singular value. So let's take this array that I've declared and invoke the reduce function, and I will then pass this method here into it. And you're going to notice it's going to take A, concatenate it to D, take that result, concatenate it to B, take that result, concatenate it to C, take that result, and concatenate it to B again. And then if I was to do this with reduce right, it's just taking this as my first item in reverse order, then doing it with C, then taking this and then combining it with B, then taking this and combining it with D, then taking this and combining it with A. And so that's why I have reduce right and just reduce. That way you can control the ordering on that. So this is, again, super powerful. I use strings so that it was very evident what's happening, but typically you'll see this more in common with numerical data. Okay, so the last set of methods I really want to talk about here are the existential quantifiers. And so when I say existential quantifiers in math, this is typically in like symbolic logic or in your discrete mathematics class, where you learn the idea that sets have the concept of all or there exist. So if there is at least one thing, then something could be true or not true, or if something is true for everything. So essentially, these are things that return a Boolean value. So again, they're both high order functions that require some other function to define a set of conditions. So here, let's look at every. So every is a Boolean result, whether all items meet a condition from the given set, whereas sum is a Boolean result, whether at least one item meets a condition from the given result. So if I have this function, we've looked at this before, given some x, x is less than b. I have my collection here. I say for this array, does every element adhere to foo? And so I define foo as x less than b. Then it's going to say false. Not everything, it's the entire array is not true based off of this criterion defined in this function. Now suppose that I redefine this function, say is x greater than empty string for every element inside of it. And so based off of what I have there, if I invoke every on that defined function, that results in true. And on the flip side of that, let's look at sum. So if for x, so given an x, is x less than b? Well, if at least one of them is, when I call sum, it's going to be true. If none of them are, so let's redefine my function. So given an x, is x greater than e? There's no e or anything higher than e. If none of them are, then it's false. So this is, and that's what existential quantifier means. It means it's true that there exists something that you're looking for based off of a condition for either all the elements or at least one of the elements. And so kind of the last thing that I want to go over in today's lecture is the idea of cascading calls. And this is why this is so important. This is why it's so critical that we went over all these methods so you understand how to use them effectively, because you're going to see them in live Java. You'll see it in JavaScript. You'll see this in probably code that we'll do in the lab, so you'll understand what's happening here. But more importantly, what makes this super powerful is the idea that we can do cascading calls with these functions. So we can do really complex statements that chain these functions one after the other. So a final note to the powerful built-in array methods: they may be cascaded one into another to compute a result. This approach of chaining function calls is the very basis for functional programming paradigms, where we can use like this stateless metaphor. So here's an example that I have. Imagine I have this array that has these 4 elements, 1, 2, 3, and 4. I can map that, right? So step 1, I start with the array 1, 2, 3, 4. I can invoke on that a map where I pass in, for argument's sake here, a anonymous function where if given an x, I will take that x and I will square it. I will go ahead and take it to the power of 2. So I map an anonymous function that returns a new array where each element is squared. So now it's going to produce a new array. So the result of this here is going to be a new array that contains the elements 1, 4, 9, and 16, right? I square each of these elements, and this returns a new array. Then on this new array, I will then invoke the reduce method. Remember, that's also a high order function. So I'll pass in an anonymous function such that given an x and a y, it will add them together. And so I will reduce the new array that I got back from this map into a single value whereby all the elements are added together. So it's going to add the 1 to the 4 to the 9 to the 16, producing a singular result of 30. And this is just, honestly, this is just a simple example of how I'm making 2 cascading calls off of a original data structure. This can get much more complex than what's happening here, but this is very powerful in how you can process data results really quickly on data structures. And that's why it's so critical to learn how to utilize these kind of traversal functions, because you can chain them together to get results without having to create large, complex, like looping logics. Okay, but that said, that is all my slides. We are done completely with talking about data structures. Next lecture, we will talk about object-oriented programming concepts with Java, including objects, classes, and inheritance. And it's my goal to get the lab for both JavaScript Basic and JavaScript data structures out within the next couple of days. And then I'll try to go ahead and create some homework assignments that will build off of those labs. With that said, are there any questions? How does everyone feel about these concepts? Excellent. Yeah, and I feel like, so fortunately, I feel like a lot of these concepts map pretty nicely to the way we handle the content in Java. So almost everything that you learn in Java 1 and Java 2, we're able to kind of directly express and articulate how it works in JavaScript. And so I think it'll be really good to get some sample labs that just have you dealing with these logic structures. And then I'll try to come up with some fun homeworks that you can do that will be pure JavaScript, where we're not really affecting the DOM yet, because after I do next, by the end of next week, we'll start learning how to use JavaScript to update our document object model and how to mutate the state of our HTML elements inside of browser memory. But I kind of want to do some things in pure JavaScript to illustrate that everything you do in Java, you can do in JavaScript without having to worry about what's happening with HTML elements. And then we'll add in the complexity of starting to manage HTML elements on top of that. Perfect. Yeah, I'll try to get those labs out for everyone so you could actually exercise everything up in preaching, and then maybe rewatch these lectures if necessary. Now, what I'm going to do is, now that these slides are done, though, I will publish lectures 6 and 7 along with the single PowerPoint onto Moodle once this lecture becomes available to me. Anyway, with that said, everyone have a good week. I will send an email out as soon as I have the lab for lectures 5, 6, and 7 available. And of course, 6 and 7 will be merged because it's technically part of the same lecture material. But I'll have a lab specifically for the JavaScript basics and then a lab for the JavaScript data structures. Excellent. Okay, let me stop my recording. Stop recording.